Hi everyone. Hi, I'm Steve Napier and I'm from Abodo and I'm based here in Sydney in Surrey Hills. And with us today presenting is Paul Reidy, a partner at Fitzpatrick Partners in Sydney. He's very, very kindly gotten on board to give us this incredible presentation, and I saw a shortened version of it and it's incredible. Just wanted to let you know, if you struggle to get the CLT test sheet, it is in the handouts. So if you're looking for the CLT test sheet, it is in the handouts. Paul, just tell us a little bit about yourself.
So I'm a partner at Fitzpatrick Partners Architects. We have our medium-sized practice here in Sydney. There's about 40 of us. We've been around for about 21 years, and I'll go into a bit more of that as we get moving.
Fantastic. Awesome. Well, as people are coming on board, we've got a few hundred now. For those of you still coming on, the test sheet is in the handouts. As you're all kind of coming on board, it's a long, very in-depth presentation, and what we are going to do is we're going to try and allow for some time at the end so that we can answer your questions. And I know there's going to be a billion questions, so please just put your questions into the chat box as Paul delivers his presentation, and I'll actually flag those questions, and we will get to those questions at the very end. For those of you, this is going to go past 2 o'clock, so it is more than 1 hour. So if you do need to leave for a meeting or something, and you aren't quite able to finish it, because this is a 1.5 formal CPD point, or 1.5 hours, you need to finish it. We will send you the recording automatically within a few hours of it ending, and then that way you can watch it in your own time as well. Now, I do want to tell you a little bit. Some of you know who Abodo is, and a little bit about what we do. We're a New Zealand company. We source a radiata pine from a plantation on the North Island of New Zealand. We only source FSC. Sourcing is very, very important to us. So it's plantation grown. And then what we do is we use high heat. So rather than using chemicals to change the structure, make it more durable, we prefer to go chemical free. So what we actually do is we use high heat, and we remove any water and tannins, so there's no leaching from the cell walls, and we then close those cell walls. So you're looking at something which is termite treated and something which is going to last for at least 30 years. Very importantly, as I was discussing with Paul earlier, is we can be used in the Living Building Challenge, and in the first parts of the journey, we are verified carbon neutral. This was just something I wanted to show you, which we completed our own cabin in Cardrona in New Zealand, and it was an exercise to really push the boundaries of our product in ways it can be used. So what you're actually looking at here is the ceiling of this beautiful building. And so we wanted to push the boundaries of different ways our Vulcan timber can actually be used. And so by the end of this project, we were actually able to store 9 tons of carbon. So we do have an EPD. So for us, we know that a square meter of cladding, for instance, is going to store about 9.5 kilos per square meter. These are just different ways that our timber has been used. So these was a block of apartments in Western Australia, supplied by Oztim, our Western Australia importer and distributor. We do a lot of school projects. We do a lot of very large sections, as well as cladding and screening and so forth as well. This is just one last one I wanted to show you. This is a project which we're working on with Smart Design Studio. And yes, the whole upper level, the red facade, is going to all be in timber as well. So what I'm going to do is I'm actually just going to share a poll If you wanted to just know a little bit more about us, I can send you a small sample, or I can just send you some digital information with our environmental credentials and so forth. So there's a poll in the section. I've just shared it with you, and we can show you more information. So before we get underway, if anyone is having issues with sound, if anyone's having issues with the video, I suggest just closing your browser, your tab, and then opening it again. The best platform to use is either Microsoft Edge, Chrome, or Safari if you're using Apple. I'm going to hand it over to you, Paul.
Thanks, Steve. Okay, so embodied carbon is a very hot topic at the moment, and something that a lot of people are certainly getting into across various different areas. Question for me, is it just more complexity, or is it an opportunity for a truly contemporary design approach? Obviously, I've got a view, and hopefully I can convince you of it. So as always with these presentations, I'd like to start with an acknowledgement of country. I'd like to acknowledge the Gadigal people of the Eora Nation, on whose land our studio is, and pay respects to elders past and present. As an architecture studio, Fitzpatrick Partners is really proud of where we are, and we understand that the land that we're working on has never been ceded, and always was and always will be Aboriginal land. So the presentation today, hopefully I'll be not too much longer than an hour. I'm going to go through a bit of climate context, which is really kind of, I guess, a broader understanding of where embodied carbon fits. Architecture's part within that, and then carbon in buildings in a bit of detail. And then I'll move into Fitzpatrick Partners, what we do, just a bit of an overview, and some case studies. The case studies are going to be the majority of the presentation. And really, they're going to focus in on a few different aspects of carbon and our carbon understanding. A lot of this is a journey where we're on our journey. We're at the second iteration of our sustainability action plan, which you can get on our website if you're interested. Which we put together over two versions of it. We started in 2021 as part of Architects Declare's call for practices to step up and really act decisively in relation to biodiversity and climate emergency. And really, this is the advocacy of today is really part of that continuing journey for us. Top corner here, you're going to see question every now and again for the questions for those playing along for CPD points. Keep an eye out there, and you might be able to match the answer to your question. So let's crack into it. I always like to start at the macro and an understanding of the planet with 9 planetary boundaries, which was defined by 28 global scientists led by Johan Rockström from the Stockholm Resilience Center. And it really breaks down the planet's systems and processes into 9 different boundaries, of which climate change is one. Those boundaries in this diagram are described as being below the boundary, i.e. safe, which is this inside green circle, extending beyond that into a zone of uncertainty with increasing risk. And you can see that climate change and land system change are in that increasing risk, and beyond the zone of uncertainty, which is high risk. And you can see that there are 2 elements that are sitting in there. That's biodiversity loss and extinctions, and phosphorus and nitrogen in our planetary systems. So while today's conversation focuses in on climate change, all of these are, broadly speaking, linked. And climate change is not the worst proposition. Biodiversity is at much greater risk, and the use of phosphorus and nitrogen in our environment, which is really an agricultural issue, among other things, are way worse. So why are we really focusing on climate change? I suspect these 2 don't impact on humans quite as much, if I'm being cynical, and climate change obviously does, but obviously they're all also connected. The other point here, looking forward with hope, is that one of the other planetary boundaries is stratospheric ozone depletion. That used to sit outside, and since we acted on ozone back in the 70s, that's come back in. So we can make a difference, and we can make things better. So there is definitely hope. The science on carbon is really, really clear. If you extended this diagram back to the 1810s or 1812s, this line basically flatlines, and it was at about 283, 282. And we've known about the science of climate change to obviously increasing levels for about the last 50 years. And in that 50-year time frame, there's been many reports and conferences and agendas and accords adopted. And the parts per million, which is the diagram here, continues to go up. So whatever we're doing, we're not doing it enough, we're not doing it fast enough, and things need to change. Now, this is a diagram from the IPCC, and it talks about the nature of that challenge or that change. And I think as architects, we need to think forward about this and understand our place in the overall world. It's a societal challenge. It's not just an architecture challenge. It's not just an architecture problem. This societal challenge gets broken down into energy, agriculture, buildings, transport, industry, and other. And this diagram actually talks about the impact of potential net reductions. So how each of those areas of society can have a positive impact on changing things. It then, the colors on the diagram talk about cost from less than the reference cost through to really quite high costs for some of the changes. The bar talks about the zone of uncertainty, the impact of those things in terms of dollars. Gray relates to where the information just isn't quite there yet to define the cost of various different decisions. Sitting within that and blowing out buildings for a second, the elements that are in here, when you start to drill into them, you quickly realize, gee, they're all about operating carbon. So that's about avoiding energy, energy efficiency, making buildings high performance, putting renewables on site, improving existing buildings, with the exception of the bottom one, which is the use of timber products, and more on that later. The rest of them are really about operating carbon. These are global numbers. These aren't specific to Australia. But I think we would all know that buildings and construction also have an impact on energy, industry, transport, and even some of the stuff that sits in other. So holistically, we sit at the centerpiece of consumption in construction, which is to say that the building site is where everything gets consumed. All of the products that we use to build the building and all of the things that we consume energy with are consumed in the building, but the influence of that is global, and both in emissions, but also in positive and negative impacts more broadly. So to just drill into the energy one, for example, and this is a diagram, top diagram I'm sure a lot of people are across, buildings are responsible for 39% of the energy-related CO2 emissions as at 2017, of which 28% is operational carbon and 11% is embodied carbon. Embodied carbon being the carbon we build from, operating carbon being anything with a plug. And where that needs to go, you can see this line follows that parts per million line quite well, and where it needs to go as of now is straight down. So that's quite a big shift. Why do we need to do it? Why do we care? Well, reducing the amount of carbon in the atmosphere obviously will mitigate the impacts of climate change. It'll improve public health, boost the global economy, maintain biodiversity, and in simple terms means that we have enough air, water, and food to be able to feed ourselves and future generations. Now, given the trajectory and given some of those planetary boundaries we talked about, the next 8 to 10 years are critical. Now, for architects, the vast majority of us, what that means is the projects that we have on our drawing boards now are at play in this space. We need to act now and act decisively. Architecture, as I'm sure everybody would agree, is an act of optimism. We project ourselves into a future that is as yet unwritten and unknown and unknowable, and we profit position as to what the buildings of the future should be. But architecture is a key contributor to climate change. So how do we square the circle on that? How do we remain optimistic and still build? What can we do about it? Well, the first thing that we can do is understand all of the various bits and pieces of jargon. So this whole world of carbon is new to a lot of people. Hint, top corner. This whole world of carbon is new to an awful lot of people. We weren't, if you went to university when I went to university, trained in this, and you're having to learn it now, and there's a degree of change associated with that, and people don't like change. But the first thing is understand the language of carbon, understand what causes it, and what the differences are. So I'm going to spend a bit of time on this slide. This slide is from Letty, which is a really great resource, and I'll touch on them a little bit later in the presentation as well. But to understand carbon, whole of life carbon is operational carbon, all of the things with plugs on it and water and various other things inside the building, and the embodied carbon, the carbon that the building is made up of. To understand that in slightly more detail, whole of life carbon is this big blue box. Cradle to grave is another way of describing that. That incorporates embodied carbon and operating carbon. Embodied carbon, drill into that one step further, has got upfront carbon. That's what we build from. That gets broken down further into two stages, the product stage and the construction stage. You'll hear a lot of talk about A1 to A3. That's where EPDs like the one Steve talked to earlier focus. That's the product stage from the raw material through to the manufacturing gate, otherwise known as cradle to gate. Include in that the construction stage, which is transport from Steve's manufacturing plant through to the building site. And then from the building site, the ability to construct it is cradle to practical completion. Go one step further and go right out to cradle to gate, or sorry, cradle to grave, and you've included in-use stage, which is maintenance, repair, refurbishment, replacement, and the end-of-life stage, which is disposal, demolition. And ultimately, in including whole of life, you also add back in the operating carbon. That gets you cradle to grave. And then the full circle is when we start thinking about a circular economy. We effectively replace end stage with thinking circular, reuse, recovery, and recycling, and that's really cradle to cradle. That diagram sums up in one piece this whole gamut of information. It starts in here. Everything that you're going to hear about embodied carbon, largely speaking, is talking about the product stage of upfront carbon rather than the holistic stage. It's really important to understand the differences. All our EPDs, etc., are going to be measuring this front bit and this front bit only. Don't lose sight of the fact that these things exist, but it's also important to understand the ratios and relationships. So they're different for different buildings. These diagrams, again, from Letty, talk about office, medium-scale residential, and schools. These are diagrams from the UK. They are pretty good reference points for Australia. We don't have similar reference points from other sources as yet. And the difference between the diagrams on the left and the diagrams on the right, this is as per current contemporary building regulations. This is the signpost of where we need to take things to. The big shift has been the reduction in all numbers in the operating energy component, B6, dropping down radically. Like to think that this would drop even more. These are targets for 2030. And then the other two components that you can see, while that's today's diagram, let's focus on this diagram, which is the future diagram, which basically rounds out to a third between operating energy, the product stage, and the maintenance and replacement stage. They're different for different types of buildings because different types of buildings get laid up different ways. It's key to understanding the starting point, but to know the path that we want to go down. And then how we can improve is by measuring, and measuring is just the beginning, because once you measure, then you act. So drilling into that one step further, looking at that embodied carbon component, this is taking the office piece. We now are talking about 48% being in the product stage, with 45% in the maintenance stage. Of that 48%, which represents effectively upfront carbon, we break that down further into the superstructure and substructure as the primary components, amounting to about 65%. Again, all of these numbers are generic. Anytime you see percentages, they're not based on a specific building, they're based on generic overall numbers, so they're important to keep some sight of that. hint in terms of question. But structure, facade is the next big one for office. Again, this is just office. Then MEP, then internal finishes. Looked at another way, and I find this bottom diagram really quite helpful. If you look at the top 5 components there, upper floors, foundation, envelope, frame, and piling, they all represent somewhere between 10 and 20% of the overall embodied carbon of the building, and they all have the biggest impact to change. Get to below that, internal linings represents maybe 7%, ceiling finishes 5%, floor finishes less, and external works less again. And then obviously the capacity to make change in these is still there, still not insignificant, but it's nowhere near as big as structures and the overall piece around the envelope and structure of the building.
Paul, just very quickly, we can't see your cursor. So
okay,
if you
right. So if you can't see my cursor, anytime I say hint, have a look in the top right-hand corner for question.
Yeah, sorry.
No problem. So who are Fitzpatrick Partners, and what are we doing about changing things? What part do we have to play? So as I said earlier, we're a firm of architects of about 40 people in Sydney. We've been around for about 21 years, got quite an established reputation across towers and healthcare and commercial buildings and a series of other things. And we've had a passion for timber for quite a long time. We developed, as part of our sustainability action plan, a series of strategies and kind of principles to work through across all of our projects. So in the first instance, looking to not build on greenfield sites or avoid it as much as possible, building in density into our cities, planting more than we remove, reusing already spent carbon, which is existing buildings, and not forgetting in all of this discussion around sustainability that we actually design for human joy and delight. The middle line is a series of moves in terms of in terms of carbon in general. The first of which is all of our buildings shouldn't have fossil fuels in them. So we seek to avoid that at all costs wherever possible. We then obviously design with minimizing energy needs as a focus. Then the use of green power, strong emphasis on minimizing embodied energy, which as you saw in those previous diagrams, becomes an increasingly large component of the overall pie. And then finally offsetting what we can't already remove. Our goal is that strategically sometime between 2030 and 2050, and I'd like to think sooner rather than later, we become a fully regenerative design practice. We are going through and measuring all of our projects. So we're analyzing our projects both against the rating tools that we're using, the star ratings within those that we're applying, but also how they're going, how each project is taking us a step closer to our journey in terms of regenerative design. And we track that across our projects as a studio. For us, data is power. We've been designing in BIM for decades. BIM is really a large data set. The ability of technology now to take that data set and strip it and analyze it in a variety of different ways really gives us power to be able to act in ways that previously we did on gut feel or rudimentary understandings. We can now do in much more analytical detail. And that really is a key driver to how we can make big steps forward in terms of sustainability and the understanding of how buildings impact the planet. So our approach when it comes to embodied carbon, then drilling into that in a bit more detail, is first and foremost to question everything. Be very careful what information you're basing your actions on. This is relatively new space for lots and lots of people. Everybody's on a journey of learning. There's nothing wrong with that. It's great to ask stupid questions, and I always am a big fan of asking stupid questions because you learn something. Learning to focus on the big wins, structure being a key one, obviously. Devise actionable approaches that remove not just principles or airy-fairy words, but as you'll see in some of the case studies I'll show in a second, really actionable words to remove and reduce carbon. And being really careful of unintended consequences because not all roads lead to the same place. The two diagrams on the side talk to how we can minimize embodied carbon. First thing is, do you need to build it? Second thing is, what size do you need to build it at? Third thing is, can you use a building that's already there? Then to target structure, then enclosure, and then really getting into the fineries of EPDs and specific products. The bottom diagram's a Leidy diagram, built same logic, build less, build light, build wise, build out of low carbon materials, build for the future, and build collaboratively. As architects, we have a great position in terms of advocacy. We also have a great position in terms of our role in construction. 80% of the life cycle impact of a building is locked in that foundational stage up to schematic design. So that's when we do the passive principles of solar orientation and wind orientation, the sizing of the building for its use, the definition of the overall aesthetic, the window wall ratio, defining the systems that are used within the building. That all happens in the bottom of that fat triangle. And then as you go further and further towards the top, you get into building, material procurement, and a whole series of other entities about design for disassembly and things like that. But the relative cost of making change later in a project, it's the same old bell curve as you've seen for many other uses. But we as architects need to realize that there is power in our position, both in advocacy and in the decisions that we make. And there's also therefore great responsibility. So let me go through some case studies. I'm going to go through, in the first instance, 73 Miller, and then step through a few other projects, and just really to give you an understanding of how these projects are acting and how we're growing over time a body of knowledge. 73 Miller, office building from the 80s, completely unremarkable to my eye. Existing lump of carbon, if you want to look at it that way. A tenant was moving out, building needed a major refurb, potentially being pulled down. The strategy that we employed was to keep the existing building and to honor all of that existing carbon, but not the existing form, rethink that, reskin the building, and come up with a new entity. In doing so, importantly, we wanted to honor the existing carbon that was spent in all of its roughness and glory. This isn't typically we talk about building reuse in either really fine heritage examples or really robust, 19th century industrial buildings with great beauty in their detailing. This was a 1980s office block built in the 1980s with the mindset of the 1980s. So what we sought to do was take it and reuse it as an entity of not heritage value, but of carbon value, of existing building value, warts and all. So we bush hammered all of the concrete walls in the lobby, including all of the bits of no, you can't see my cursor, sorry, not much point in me pointing, including all of the little knockoffs and little areas of imperfection, and really played them up against the new finishes that we brought in. So we had this really strong relationship between existing building that was there as a reality, and the new elements that got brought in to bring to life a new office component. So the outcome of that was that we took 15,000 square meters of an existing 1980s building, let's call it a carbon sink, and we reused the existing structure, some of the services, and we took the material that was the dominant material in that being concrete, and we honored it in the narrative of the building. So it became this kind of unique positioning for the building because we kept the existing 15,000 square meters. We then added 4,000 square meters and were able to achieve a structural carbon for the overall 19,000 square meter building of only 21 kilograms of CO2 a meter squared. That's ridiculously low. But it was only that low because we reused 15,000 square meters of it. So the outcome is a new office building designed for the future, 5-star Green Star, using green power, really set up well, that only used 4,000 square meters of structural carbon and reused 7.1 million kilograms, I always get that wrong, million kilos of CO2. So a really good outcome. Second one is a building that's just gone in for DA in Ultimo. And again, it's a similar strategy, similar mindset. We've got the ugly duckling building in the middle between two heritage items, two really fine heritage items on Bay Street in Ultimo. The building in the middle is a 4-story building, 3 stories here and 1 below, in concrete from the 60s. It was a detracting building in the urban environment, according to council. Couldn't agree more. But rather than having a solution that pulled it over and put a new building in its place, we sought to again reuse that existing carbon and avoid needing to use more. In order to solve the contextual proposition, we added to the building. So we added 3 stories on top of the existing 3 or the existing 4. Picked up on a lot of relationships with the facades of the 2 adjoining buildings to provide a building that really sat well in its context. In having the opportunity to reposition the building completely, we worked with the existing structure, but we cut a hole in it for a light well. That gave us the ability to cross-ventilate the building. We put solar farm on the roof. We had a real focus on the embodied carbon. Obviously, it's a fully electrified building. And as we tend to do with all of our projects, we've summarized it in a slide like this, where we've summarized the key ESG initiatives along the side and really focused in on how the building can have a positive impact. So you can see that we kept on the section on the right-hand side, we kept the car park level, replaced an awful lot of car park with end of trip, maintained 2,200 square meters of office space on the next 3 floors up, cut a courtyard into it that then meant all access via the lifts was through this central courtyard, allowed us to naturally ventilate the floors, and then added on top of that 3 floors, accounting to about another 2,000 square meters of floor plate. Top 3 floors we did in timber. The bottom floors we maintained in the existing concrete. In doing so, we analyzed the building relative to an alternative. So as it says here, we saved 46% in embodied carbon by doing it in timber. Another way of looking at that is, if we did it in timber and that was the base case, had we chosen to do it in concrete, we would have added an additional 80% on top of the carbon necessary to build it in timber. Why would you do that? The ultimate solution here saves 450 or avoids the spending of 450,000 kilos of CO2 for a really small, modest building. So scale isn't necessarily an issue. We can do it at any scale and we can have an impact no matter where we are. Timber is a key theme for us. We've been investigating timber for 15 plus years now across all kinds of typologies. These are all buildings that in one way or another integrated timber as part of the solution, some built, some not. We are at the point of really being a timber first practice, and that comes from a carbon centric logic, but also the beauty of the material. And hence we're very aligned with Stephen, with Abodo, in terms of where they're headed as well. So with timber first as an approach, we're very proud of buildings that we're just finishing now in timber. This is the Bond at Northwest, our first completed office building, full office building, I should say. We've got one around the corner that's much smaller, a little office building as an extension. Part of that timber story comes to this diagram, and I'll put this diagram up again later, but this is from our embodied carbon calculator internal to Fitzpatrick Partners. The red line is Letty's 2030 target in terms of structure and embodied carbon within structures, and the highlighted elements below are buildings where we've employed timber as the primary tool to get us below that line. Timber is not only beautiful, but really practical as well. I'll come back to that diagram in a bit. So next case study. We're flying through these, Steve. Got no problem. Next case study is structure and apps. This is 44 Waterloo, which was an office building we did somewhere in between various COVID lockdowns at Macquarie Park. We did the design for this. It's about an 18,000 square meter office building, one of 3, the first of 3, 5 generic speculative office building, so 5.5-star neighbors, conventional low temp, low flow VAV system is the mechanical solution. Its orientation is about 45 degrees to north. And again, you can see the summary of the various ESD initiatives that we've undertaken on this project. I'm going to focus in on 2, the first of which is about structure and again, carbon. The second of which is about the facade. We also spent a long time focusing on things such as providing outdoor space on every level for tenants, having a human scale base to provide activity, both focused on trying to get people back to the office and out of home. Excuse me. We also looked at central atrium for passive return air. The structure at the bottom left-hand corner was a big thing, understanding it, pulling it apart, trying to get the best out of it, and then operating carbon in terms of the facade will be the second thing I touch on. We did a study with, as part of Architects Declare, a group of 5 different firms teamed up with 5 different students to understand embodied carbon using eTool. So we had a great student who worked with us from Sydney Uni, who worked through with us the 6 or 7 images on the screen here, the structure that lies behind them all, starting with the benchmark, which is where we thought we would be, a 9 meter by 13 meter concrete grid for the building, and then working our way through a series of different solutions from pure timber to timber concrete hybrids to entirely option 2 in the middle there. The 28.5% saving is all concrete, but an 8.4 by 8.4 grid rather than a 9 by 13 grid. And that was a real eye opener, that just by changing the grid and understanding the design in that regard, not working with material at all, we could make significant savings in the embodied carbon of the building. And that really talks to efficiency and where we do and don't use it. And with all of these numbers going across the board, we were able to benchmark them relative to the starting position on the left-hand side. Diagram on the bottom just reminds everybody that we're talking about that 48%. So this is the biggest moves that we can make on the biggest component we can make at the start of a project. We can look at those across square meters as well, rather than across the whole building, and bring it down to a per square meter kilograms of CO2 that's in the structure. That's again really useful because we can now benchmark across multiple projects. So doing this exercise, we learned an awful lot about not only which one is best and why, but also where the carbon is in each of the options, what the difference is in end of life versus start of life, and a whole series of other things. But the study took quite a while. It was 4 to 6 weeks, I think, to do. And we asked ourselves, how can we have this level of iteration on projects more quickly, internally? Do we need to go to eTool, or can we develop our own app? So we devised all of this understanding. We had learnt, I suppose, the basics. And then from here, we launched into developing an app that would allow us to gain similar levels of knowledge more quickly and iteratively across projects. So the app is at, for those of you with a pen in front of you, www.embodied-carbons.com. And it very simply takes the structure that we've already modeled well in BIM, takes an Excel spreadsheet of that structure as volumes effectively, drag and drop that into that blue box in the middle there, and it immediately represents that in 3 different data sets. The 3 data sets that we have internally are the ICE data set, which is publicly available, the EPIC data set, which is publicly available, and Greenbook, which is subscription data that we've got from Greenbook. So all 3 data sets tell slightly different stories. And it's not for us so much the question of which one is right. None of them are, because all 3 of them are generic numbers. So by definition, they're not right. But it's getting relativity. So why is the ICE number 6.5 million kilos when the EPIC number is 12 million kilos and the Greenbook number is 9.9 million kilos? In order to understand that, you need to drill into what are the 3 data sets measuring. It's a very interesting rabbit hole, but one I'm going to avoid just for today. The other things that the tool allows you to do is to look at the various building elements, beams, columns, slabs, walls, stairs, and be able to adjust the materiality. So we can go from 50 MPa concrete to 32 MPa concrete and see what the impact of that has on a kind of a live counter down the bottom here. We also have the ability to have conversations with our structural engineers about RIO rates in the various entities and understand the impact of them. Because when you look back at, if I go back a page, when you look here, the yellow bar is actually reinforcement steel. So there's quite a large amount of it is sitting in that. Now, you've seen this diagram already. The great thing about this tool now, this is our internal version, our external version doesn't yet have this, we're still working on that, is that we can benchmark across projects at that per square meter rate. So we can see the ICE information represented as the blue cross, the EPIC information as the purple box, and the green dot represents the Green Book information, and you can see where they sit relative to each other. You can also see, and these are all live projects, so from left to right, the first 5 are the 44 Waterloo project that you've already seen. The next 2 are 73 Miller, both as proposed and as original. So the carbon that's in that is really the gap between those 2 numbers rather than anything else. The next one with the double circle around it is Bay Street. So that's, again, a reuse project. And on the far right-hand side is the bond. So we can see across all of our projects, quite openly and quite truthfully where the carbon is, and which projects are performing better than others. And we can, over time, start to understand why. For example, the third one over from the left is one of the options for 44 Waterloo, but only to ground, whereas the fifth one over is the actual option that we went with for 44 Waterloo, but including the substructure. So you can see, even including for a very large basement, that fifth one is better than the third one. So really starting to understand and drill into those numbers is quite a powerful thing to be able to do. And a really good exercise from the point of view of that project. Now, I'm going to shift gears a little bit to go to same project, but talking to Embodied and operating carbon as the point at which they interact. And that really is about the facade. So the purpose of a facade is to connect us to the outside and at the same time to separate us from the outside. Window wall ratio is the primary thing that we use to do that. And there's a lot of things that go into window wall ratios. This is an office building, so we'll talk to some of the marketing considerations for office. Any of our leasing or tenant clients would say to us, floor ceiling glazing is great. I want to be able to get panoramic views. I want to get connection to the outside. That's all fabulous. But from all of our services consultants would say to us, solar heat gain, we need to respond to the orientation. We've got too much glass is bad. There's different embodied carbon buildups in different materials. In Australia, it would seem at the moment, the norm for office window wall ratios is somewhere around 70-75%. Interestingly, in the UK, the norm is more like 30%. So they still lease office buildings in the UK. They still have, a connection to the outside. It's just different. So this office building, we're gonna drill in now and look at just one bay, but we're going to look at it from an operating performance. There's 2 things at play here: insulation and shading. Insulation is defined as U value, and shading is generally defined as SHGC. So U value is, as lots of people will know, is the resistance of a material or buildup to the transmission of heat from one side to the other. Heat moves, cold doesn't. Shading is a number of different things. It's first and foremost, how much window have you got in your wall, or window wall ratio. It is the external shading that you put outside the glass, and it is the solar heat gain coefficient of the glass, which is a percentage measure of how much heat, solar radiation, a glazed facade allows to pass from outside to inside. So let's have a look at that typical bay. Double story bay. In this instance, the one that we'll analyze is a single story bay. It's got a 50-50 window wall ratio, thereabouts. Insulated panel, quite heavily insulated on the inside of the solid elements. High performance glass in the main DGUs in the main facade. When you look at it from a U value point of view, and you break it all down, the 2 charts at the bottom, on the left hand side, you've got the area by material. So the big blue one is glass. The next one is the solid spandrel in orange. The next one is the solid curtain wall section in gray. And then the mullion area, which represents about 9% of the overall area. On the right-hand side is the actual performance of that facade. So how well it's performing in terms of U value. What you see shift is the 9% of aluminium frame represents 54% of the performance number. In other words, it's performing really, really bad. The 52% of glass is representing 35.64% of the overall performance number. And the 2 solid bits are generating very little, 5 and 6%. So what you can see here is glass bad, mullion really bad, solid really quite good when it comes to U value. So thermally broken frames are better than aluminium frames. Less framing is better than thermally broken frames, and probably timber framing is better than both of them if you're in an environment where timber framing is allowed on the external envelope of a building. To then look at shading, this is the next layer in. So SHGC tends to be directly inversely related to VLT, which is visible light transmission. What that means is the higher the SHGC, the better it performs, the glass, the darker it is. But you could also use lower window wall ratio, higher window wall ratios, which means less glass, which means that you could go for clearer glass. But there's those market pieces around window wall ratios. So all in all, we're trying to strive a balance within operating energy. But let's have a look at the other side of the coin now. Let's have a look at the embodied carbon of the same facade. Hopefully that's telling us the same thing. So typical, this is ignoring the frame for a second, because the frame being an aluminium is a bit of an outlier. So to just look at the solid panel itself, a typical double glazed unit will be about 139 kilos of CO2. These numbers are all EPIC-based numbers, by the way. A typical DGU with a spandrel, so as soon as we put that next layer in behind it, it's jumped to 390 kilos of CO2. If we replace the outer layer of glass with aluminium skin or Equitone or Fiber C or terracotta, you can see the numbers jump around there between 470 and 290. Even an internal lining's got 71 kilos of CO2. So the lowest embodied energy of the external envelope pieces, the first three, is glass. But glass has the highest operating cost. So now we have to balance between operating efficiency and embodied efficiency. So we developed a calculator. This is a rhino and grasshopper calculator. We haven't actually made this publicly available, but I can't really see any reason why we couldn't. So if you want to, let us know and we'll let you have it. We developed a calculator to just look at a typical bay. Now, the reason that we looked at a typical bay as opposed to the previous calculator that looked at the entire structure is because we tend to model relatively inaccurately in facades and relatively accurately in structure, i.e. we put a box section to represent a mullion rather than something with all kinds of flutes and screw connections and everything else in it. So the order of accuracy is slightly different, but it allows us to get a sense of relativity. So the 100% glazed area would be 139 to 150 according to the EPIC data set. And using the same data set, we looked at a framed version and we're up at 338. So you can see the difference there is just the frame. So if there was an entirely glass facade, 6 panels across this one bay of the facade, it would be 338 kilos of CO2. If we made it a solid shadow box, it's now jumped to 409. If we make it larger panels rather than smaller panels, it goes back down to 400. So what's actually happened here is you've saved 20 kilos in relation to aluminium, but you've spent 10 in making the glass thickness slightly thicker. So it's still a net saving, but we're at 400. We still have, you know, a 70% glass facade. If we introduce a solid section, we're now up at 450 because the solid section's got more in it than just glass. If we make that solid section out of terracotta rather than out of aluminium, it's now back down at 420. If we include an aluminium sunshade, it takes a big jump to 518. If we put that aluminium sunshade around every frame, we're up at 823 kilos for the same facade. If we make all of those pieces out of terracotta, we get that back down to 478. These are all relatively rubbery numbers, but you can see that the higher performing facade in terms of operating carbon is actually a lower performing facade in terms of embodied carbon. So how do we compare? Well, 478 was where we ended up on that last slide. If we look at Green Book's benchmarks, they would say that a 3-star office building should have 480 kilos of CO2 in a meter squared, 4-star 380, 5-star 290. So after putting in all of this time and effort, we're sitting at just better than 3 stars, which is pretty disappointing. But when you drill into the data a little bit more, you realize that Green Book uses an assumed number for aluminium of 15 kilos of CO2 per square meter, and EPIC uses somewhere between 26.7 and 32. So when we change our numbers and we use Green Book's numbers, and we use 15 kilos for the aluminium, we get to 362. So now we're better than 4-star and on our way to 5. That's really good. But remember, in pure embodied carbon terms, an all glass facade would be 229. So an all glass facade would be better in embodied, but not better when it comes to the balance. So you got to be careful what you measure. You also, in relation to using different data sets, need to be careful what you compare against. A note here just about overall kind of balance, right? We still design for human joy and delight. We could make this better by having a window wall ratio with less glass in it. We could make it better by having a floor to wall ratio that was more floor to less wall, i.e. we could make it that the building was fatter and people were further away from the glass. The balancing factor there is we need to get to daylight autonomy numbers. Green Star would suggest specific numbers in relation to daylight autonomy, so we can run that calc and we can say, well, where do we sit? Holistically, it's about balance. It's not about being all on embodied or all on operating or all on ignoring the human. So let's look at the operating component of that same facade. And what we're going to try and do now is cross the streams, right? So we get an understanding of whole of life carbon rather than just operating on its own or just embodied on its own. So remember, the building's 5.5-star neighbors, so it generates in the order of 1.1 million kilowatt hours per annum of electricity. Over a 50-year life, that's 55 million kilowatt hours. Temperature control, i.e. moderating the internal environment for humans, represents, generally speaking, about 60%. And that's an average, but about 60% of that number. So let's just work with that for a second and jump down a couple of numbers. You'll see that 33 million kilowatt hours would relate to temperature control in the design life of this building. With the greenhouse gas conversion factor of New South Wales at 0.922, when we did this study back in 2021, that gives us 30.5 million kilos of CO2 associated with keeping this building at the temperature that humans like it for the life of the building. So therefore, if we look at the impact of putting a sunshade on the outside of the building, we can see that we could make further savings to that 30.5 million kilos. For a 200 mil shade, we could save 7%, and all the way down to a 1 meter shade could save 23%. So that's a saving of somewhere between 1 and 7 million kilos of CO2. And as you can see on the graph on the right, there's a crossover point. What that crossover point is saying that the biggest sunshade starts with the biggest amount of embodied carbon, but at a point in time, that saves more energy than it uses in the upfront. So that diagram looks like it makes some sense. But, and it's a really, really big but, the 30.5 million kilos of CO2 assumes that the grid stays the same. The grid doesn't stay the same. So the grid was 0.922 when we did the exercise. I looked the other day, it's 0.79 at the moment, but that number is already a year old and it's continuing to change. The diagram on the side here is on the left-hand side, closure of various coal-fired power plants, and on the right-hand side, the introduction of various renewable energy zones. Both of those diagrams are from AEMO, they're not my numbers, but the grid is changing and it's changing quickly. If we followed those as just a continual line, that would take us from 30.5 million kilos to 8.5 million kilos. What that looks like is quite dramatic, but the change is even more so. So you can see here the grid from 2023 through to 2050. The grid, the red line is the amount of carbon intensive fuel sources, and above that line is renewable. So you can see the amount of energy is going to grow and grow quickly, but the operating carbon, which is the carbon in that energy, is going to drop. So operating carbon is cumulative over time. Upfront carbon is spent the day the building is built. Therefore, the carbon intensity of the grid has a real impact on our overall balance. Carbon intensity of the grid has a big impact on operating, but has no impact on embodied. We're going to get to 82% renewables by 2030 on our way to net zero. Therefore, the operating carbon becomes less of a focus in trying to get to the right answer than the upfront carbon, even today. And if you designed a building to use green power, as I said earlier, then there is no operating carbon from day one in principle. So really the embodied carbon or upfront carbon piece becomes very much the focal point. Now, there'll still be a desire to build efficiently, and that'll probably come from things other than carbon. Energy stability of the grid, responsible energy use, and energy equity between users will be really important, and they'll probably drive rather than pure carbon reductions. Upfront carbon, the bit that architects deal in, that's going to become really key. Here's what that same graph looks like if we take it to 8.5 million kilos. Two things to note. One, the lines go flat after a point at about 2050. You guessed it, that's when there's no carbon in the grid anymore. So you're not saving carbon. You're still using energy. The energy numbers would still follow as per the chart up the top, but there's no carbon in that energy anymore because the grid has changed. So the context into which you are building has changed. So the second thing to note is that the lines didn't cross. So with an aluminium sunshade, doesn't matter whether it's 200 millimeters or it's a meter, you don't say, because the grid is greening and is therefore decarbonizing, you don't save the embodied carbon that you invest. In other words, you spend more upfront than you ever save over the life of the building. Now, that's still assumed. The steepest part of that curve is the very start of it in 2021. The building's not built yet. So theoretically, if that building was built in 2025, we're already partway down that curve. But we asked ourselves the question, well, what would happen if we were able to just, let's say, halve the amount of carbon that was in the sunshade? And what you can see there is the bottom diagram, which is terracotta. It does cross the zero line and the curve does shift. So you would save more carbon overall in the larger sunshade, but given that it passes zero, that's a theoretical saving, not a real saving. So once you pass zero, any of the savings are kind of moot. So what we ended up with was a terracotta sunshade rather than an aluminium one. Obviously, it was minimized in terms of area to get Section J compliance today, but the context is really, really important. The greening of the grid made way more impact than anything we did on the facade. So now you're back to designing for all of those other things: human comfort, adjacent the facade, the right window wall ratio to be able to get connection to the outside, but still having that energy balance. That's the ultimate facade that we ended up with. That went in terracotta. Some of the takeouts from that, that was a bit of a deep dive. Some of the takeouts from that one are accurate measurement. The quantities that you take off are key. Shit in, shit out is the old way of saying that. Whose data and what standards you use. Don't try not to cross the streams. Don't use EPIC's data in Green Book or ICE's data in EPIC, or it just keep linear within one data set. Ideally, EPDs are more accurate, specific to one product than generic data sets. What's included? Are you including just being consistent between just structure above ground, not including substructure, all of those things? The study timeframes that you talk to, so A1 to A3, or are you including construction? Is it cradle to gate, cradle to grave, cradle to cradle? Sourcing sustainable materials. I'll give you Steve. FSC certified timbers, greener production energy. There's lots of, when you start to understand your supply chain as an architect and the impact that you have going up the supply chain by asking strong questions, by demanding more from your suppliers, it was really interesting where it goes. The more of us that do it, the more impact, Steve's nodding, the more impact people like Steve in his position will take and will change overall. Long-term considerations. We need to design for disassembly. We need to design for circularity. What different materials have different end-of-life outcomes. Timber can be reused at the end of life. Concrete can be crushed and downcycled. Really, that's all it can do. And the other thing to not feel comfortable in is the building code. The building code is by definition behind all of this. It's playing catch up. So it's not there yet. Okay, a couple of more to go. Steve, I think I'm doing okay on timing, am I? Okay, good. So this is a DA that just got lodged in North Sydney. We're going to talk just facade material here and the impact of putting this data in front of clients. So two versions of the same building, aesthetically identical, materiality different. So on the left-hand side, an aluminium version, and on the right-hand side, a GRC version. The detailing, obviously, the GRC is going to be different to the aluminium, but in terms of the window wall ratio and the aesthetic outcomes, they're very, very similar propositions. So we went through and we analyzed the two of them from different views, different angles. Obviously, these are just illustrative images to say to the client, we'll provide you with the same building with a slightly different aesthetic. We dumped them into our embodied carbon calculator for facades. We took an assessment of the two different systems and their impacts. We then weighed them up against each other and realized that the GRC version would save about 40% embodied carbon versus the aluminium. That's 3 million kilos compared to the alternative. That's quite a lot. But we also had them priced. And the GRC version was about 34% more expensive than the aluminium, or $2.35 million more expensive. So we just presented the data openly to the client. This is the embodied carbon number. This is the cost difference. And somewhat to our surprise, the client chose the less carbon intensive version, but the one that he recognized was $2.3 million more expensive. And he knew that he could make that money back in marketing the building, even if that was leasing up the building quicker, leasing it for a higher dollar, because he had a building fit for the future. Clients are aware of this. We as architects need to be as well. And by putting the data in front of him, he made a call, and he made the right call in my view, but he made the low embodied carbon call, slightly higher cost call, but a better call. And that just goes to show the power of having the data, doing the measurements, and then putting it in front of people honestly. Not every situation is going to work out like that, but that was a really good win. Okay, last project then. How am I traveling on time? Pretty good. This is a living building project living building challenge project that we're doing in Perth at the moment, and a really interesting case study for lots and lots of things. For those of you that don't know, the Living Building Challenge is a ratings tool set up across 7 petals: place, water, energy, health and happiness, materials, equity, and beauty. It's divided into 20 imperatives. Today, I'm going to talk to you about imperative 11, which is the embodied carbon footprint analysis that we've done, just to stay with the theme of the rest of the presentation. And the thing about Living Building Challenge is it is really very holistic, end to end, includes, beauty, inspiration, education components, includes everything from water and energy the whole way through. This building is going for all 20 imperatives or full Living Building Challenge certification. It's a very big ask, but some of the things that we're doing, just in brief, we're providing 105% of our own power on site. You guessed it, lots of solar. We're capturing and using all of our own water. So the Living Building Challenge takes the philosophy of a tree. A tree can grow as large as the nutrients and water it can gain from the place that it has, from the sun that it can gain landing on its leaves. These are the things that define the scale of the tree. The same thing could and should be true for architecture. So this building will generate all of its own power, capture all and reuse all of its own water. In order to generate all of its own power, obviously there's a really big impact on reducing the amount of power that the building needs, which is that 0.3. Today we're going to talk about 0.4, and just the first of what I hope are many pieces to come out of this project, which we'll share in the future in terms of the embodied carbon study that we've done. Then we're going to, it also obviously optimizes for transport, supports a heap of biodiversity. There is 10% of the site given over to urban agriculture, and we hope becomes a great place to work. So the study that we're going to talk about today in the next couple of slides, not many, is an analysis of the ground floor slab. We couldn't put timber in because it's the bit at and below ground. So we analyzed 9 different options, from a PT banded slab to a flat reinforced concrete slab, flat slab with drop panels, a banded one-way slab, a PT flat slab, etc., etc., etc. You can read them down the side. We analyzed using our embodied carbon app the amount of embodied carbon in each of those options in a 2-bay representative grid of the building. So here we weren't looking at pure numbers, we were looking at relativity. So you can see that the highest option, this is on the big assumption of using conventional concrete and conventional steel. The worst case scenario at 73,000 kilos was option 9, which is the brick arch and steel structure. The best option was option 8, which is a bubble deck structure, which is quite deep bubble deck structure, and then followed along by option 3, etc. And all you can break down between them the different materials and the impact of those materials in their total embodied carbon. We then took, we've been researching on the project the use of Wagner's zero cement mix, so replacing cement with other materials. And so if we went to a zero cement concrete and conventional steel, what changes in the numbers? Well, if I go back one, we were at 19,000, option 8 was at 19,000, option 3 was at 20,000 kilos. It drops by half. So that is a really big impact. We needed to check with option 8, the impact of the bubbles. We weren't 100% sure of that. But the difference between option 8 and option 3, which is a very conventional system to fit the market, was quite little at that stage, 300 kilos across those 2 bays. The steel component, the brick arch version at the bottom here, still had a very high number, and you can see the vast majority of that is steel. We then said, well, what if we could get our steel from reused sources? Again, the relativity of the numbers is really important. The steel option has now come into 12,800. So still higher than the alternatives, but really quite low. The option 8 stayed at 9.5 because there was no steel in that. Option 6 comes in at, option 6 being steel beams and metal deck, comes in at 6.8. In order to do that, we've had to look at reusing existing steel. So we worked out how much steel is involved, and we're currently away looking at, is it possible, what's involved in getting and recycling steel into a building, and our structural engineers are working with us to determine if that's possible. But even if we ended up back at option 3, which is where I suspect we will be, we're still at half the carbon we were when we started by pursuing the zero cement concrete. There's real power in being able to understand all these numbers, being able to assess the different strategies against each other, and being able to start to look holistically into the overall proposition and where it sits. So at the moment, we're leaning towards option 3 because it's conventional, but we're still researching option 6 and indeed option 9, although option 9 probably goes by the wayside, but option 6 to see if we can get that reused steel and get that number down by, again, another third. So with that building then, we're also assessing all of the materiality. So what you see here in front of you is rammed earth in pink, concrete in blue, zero cement concrete, blockwork or a blockwork alternative in green, and timber, which is the vast majority of the timber, or vast majority of the building above ground, in yellow. So what all of this study has proven is, strategies around carbon are really key in terms of the embodied carbon piece. Our strategies on this site include, can we reuse the excavated material so the building sits in an environment of sand and limestone? Can we reuse the existing materials? We're investigating with concrete suppliers the use of that material back in concrete, but also with rammed earth suppliers using that material, crushing it locally and being able to use it in rammed earth walls. We're doing a tie-up or working on a tie-up between Wagner's and a local supplier to produce 100.
Paul, can you hear us? Because you vanished. I'm not sure what happened there. We've lost him. Oh, there he's back.
I dropped out. Sorry.
Okay, all good, all good.
Disappeared there for a second. Sorry. Didn't touch anything, I promise. 100% cement replacement in the concrete, which is really exciting. Maximizing the use of timber in the structure. We're doing the assessment at the moment now to find out the exact percentages, but a radical reduction in embodied carbon. First round of numbers look like an 80-odd% reduction in embodied carbon in the building overall. Obviously, we'll aim to make that lower, but we're also then starting to look at design for circularity, design for disassembly. There's some really big opportunities in a building of this type. So where are we at? Regenerative design is our goal. This is a great diagram from Living Building Challenge that, code compliant design is improved by green design, which is improved by high performance design, but they're all really versions of less bad. Sustainable is a really modest proposition for us. To be sustainable means that we sustain our position on the planet. Surely we would aim for more than that. We would aim to thrive. We would aim to flourish. We would aim for, really broad improvement in all of our lives. And that really is where Living Building Challenge goes, and where we're seeking to try and take a lot of our work. Big shout out to those LEDI guides. If you're not across LEDI, they're really good series of explainers and guides to be able to delve into and get your head around some of the numbers and a lot of the complexity that is involved in embodied carbon. So I hope with all of that, we've kind of proved up a little bit that embodied carbon is not just another thing to be understood and absorbed into the architecture process, but actually is a really big opportunity for us all to be able to design in a really contemporary fashion, shift maybe what we think of as great design, understand an aesthetic for today and moving forward. So as Maya Angelou says, and I love this quote, do the best you can until you know better. Then when you know better, do better. That really sums up, I think, architecture as an optimistic movement for the future. Thanks.
That is outstanding. I feel really dumb if I just clap, but I feel like I just have to clap, and I feel like everyone else is clapping as well. So thank you for an outstanding presentation. Oh, great. If you open the chat box, you see everyone is clapping.
Thank you very much.
That was, wow. There were some really good questions. One of them was, what is the benchmark carbon intensity kilograms per meter squared GFA you're achieving for the LBC in Perth?
Good question. We're working on that at the moment. The benchmark building is a conventional building built on the same site at the same size, using what you would normally do. So it's a concrete frame building. The version that we're doing is, we don't actually have the numbers yet, so this is a dodge rather than an answer. But I'm happy to answer the question when I get the numbers. But yeah, it's aiming at really taking a radical reduction to that number relative to the benchmark. But ultimately, for me, the benchmark is 0. You're not going to get there, but get as close as you can.
Yes. Very good. Daniel just asked, when using your app, is there a pro forma for the schedule file which needs to be dropped in?
Yep, there is. On the app, if you go to how to, there's quite a lot of information on that. We use ArchiCAD as our platform of choice, but in principle, if you set up the schedule to reflect the schedule, there's a couple of example schedules there as well. If you set up the columns to reflect the same thing, you'll get an outcome. And if you've got any problems with it, give us a hoy and we'll see if we can help you.
Awesome. For the North Sydney case study, was there a GRC version that had a fire engineering solution? No,
because all of that GRC sits outside the line of the envelope. So it wasn't, in neither case were they fire rated. So no, there wasn't fire engineered solution for the GRC. So when I say GRC, I mean a panel like a Fiber C or a Bearstone or one of those kind of products. I can't remember which one exactly we used. I think it was Fiber C that we used the EPD data for to do the analysis.
It's really interesting that GRC, I'd actually never heard of it, and we were working with Smart Design Studio on the the library down the south coast, and it was either our timber or the GRC, and the timber came in like they saved a lot of money, like
You
in the
would.
millions of
It's
timber as opposed to GRC.
it's another thing that I think there's an advocacy piece needed for architects in general, but timber, the Perth project, for example, we can't use timber in the skin of the building. I can make the structure out of it, but I can't use it in a facade. So I can't have, we were originally pursuing it because a timber mullion performs from a U value perspective, like streets ahead of an aluminium mullion. And we were originally using it with that in mind. But from an aesthetic point of view, we'd also prefer to use timber as a cladding, but we literally, because it's flammable, we're not allowed in Perth. So in the other states of Australia, to the best of my knowledge, you can use a performance solution to get there, but in Perth, in WA, they've actually barred the performance solution. James Fitzpatrick, my business partner, is in Scandinavia at the moment. If you've anybody who follows him on LinkedIn, you'll be, or Insta, you'll probably be inundated with images of timber buildings. Timber is something that we shouldn't be as afraid of as we are, in my view.
I've been thoroughly enjoying his journey. Do you include biogenic carbon as a credit in your embodied carbon figures, or do you treat it as a separate metric as it comes out?
Yeah, it's interesting. So the different case studies have kind of worked different ways on that. So with the Perth project, we will be, because we're doing a full life cycle on that, we will be, whereas on all of the other ones, we don't, because we're only analyzing A1 to A3. So you can't take in the full kind of sequestration piece without knowing what the end of life is.
Right. This was a really interesting one. It'd be good to compare embodied carbon in concrete/masonry building that's built to last 200 years versus timber building that'll last 100 years. That's an interesting one.
Yep.
I mean, what do you look at as life cycle with timber in your buildings?
Well,
I mean, the Japanese buildings have been standing, what, like 700 years?
100%. So I guess there's a couple of really big assumptions in that. One is that the building will last for 200 years or 100 years anyway. There's buildings about to be pulled down in Sydney that I know are 30 years old or a little bit less than 30 years old and are perfectly fine workable buildings. It's just that you can now build something on that same site that's 5 times the size and therefore 5 times the value. Nothing wrong with the buildings. The buildings haven't failed, the materials haven't failed. So in a way, design for circularity is probably more important, and design for disassembly and reuse is more important than design for longevity. I say that from the point of view of thinking out 100 years or 200 years. If you look at a facade, if you design a building for 50 or 60 years, and the assumption, the reason why that maintenance number is quite so high in the overall embodied carbon is the assumption on the facade is that at least once in that lifespan, it'll get replaced. Now, the reason that that a typical facade in a typical office building gets replaced is that tiny little 10 millimeter spacer that holds a DGU apart starts to break down, or the connection between it and the glass starts to break down. And what do? We take the entire assembly, glass, aluminium, whatever else it's made of, and the little thing that's a problem, and it all gets replaced. Regardless of what you do with that first bit, it all gets replaced. It's kind of a bizarre system that we've set up with curtain walls in particular, but assemblies in general. If we can remove assemblies, or we can make it that assemblies can be maintainable, then we can have the embodied carbon of materials last for much, much longer. But when you get out to that, is a 100-year-old building design for 100 years better than a building design for 200 years? It depends on so many other factors. If it's in an area that's growing, or if it's not, if it's a building that's going to come under pressure from macro things that it's not a part of, then maybe the extra investment to get from 100 to 200 years was actually wasted rather than wisely spent. So the context is, and it's a debate. There's no straight answer to that, but the context is hugely important.
It's really interesting. I mean, we kind of have this narrative that, timber buildings just simply will not last as long as concrete. And in fact, we've only really been building with concrete in the way we have in the last, 80, 100 years.
Yeah, I mean, the Romans building concrete
timber
will be what somebody will put in the chat, I've no doubt. But You know, it's not a case of one's better than the other in terms of longevity. As you said, there's Japanese buildings, there's buildings from the UK that are around for 300 or 400 years that are built in timber. I'll tell you the one thing though, beautiful buildings don't get pulled down anywhere near as much as ugly buildings get pulled down.
Correct.
So if we design beautiful buildings, the chances of them being, and properly beautiful buildings, the chances of them being pulled over are a lot less.
Yeah. This was an interesting one, is a balance of cost and when it comes to material selection. So Gary just said most of the times the material selection obviously affects the project cost. What are your suggestions to find a good balance between project cost and material selection to reduce embodied carbon footprint? How do you navigate that?
I start with the biggest number. So, and when I say biggest number, biggest embodied carbon number. So let's just take typical building. Let's say it's concrete. If concrete is going to be the place where you've got the most embodied carbon, it's where the smallest change will make the biggest, smallest percentage change will make the biggest percentage impact. So rather than changing out facade materials, if you can change out concrete to something that's got a lot less, if facade is 15% and concrete represents a large portion, or structure more to the point, not just concrete, but structure represents a large portion of 48, 50, 65% of the overall embodied carbon. That's why we started with what we started with, and we focused in on that structural carbon, because that's where you can make the first, deepest, biggest savings. And you're quite right, dollars definitely count. The other thing I should say, that the higher number than that is to reuse existing carbon. You know, you don't have to spend it a second time. Now, often when doing that, you need to be really mindful that a refurb project can be more expensive than on a square meter basis than a knockdown and rebuild of the same building. So it's a balancing act. But yeah, I hear the point. I hear the point about dollars completely. And really, you know, if you think about it, if you've got a bill of quantities and you've got a bill of carbon, which is the same thing with a different multiplier number at the end, rather than being about dollars, it's about carbon in the last column. You can very quickly see where, if we make this move, it has this impact. If we make that move, it has less impact. But you can only get there when you start measuring it. So there's a number of quantity surveyors around now who are producing bills, or indeed even early stage cost estimates that include for carbon. I know Slattery's have one, I know RLB have one, and I think a couple of others do as well. So you can engage in this, but when you start to understand where it is, you can then start to understand the tactics of pulling it out.
That's awesome. We'll just kind of start bringing things to a close. Some of you wanted to know some of the answers for the test sheet. So for question, and just quickly, it is entirely my fault. At the very top of the question test sheet, it's got topic detailing feature timber in architecture. That's my wrong. It's actually not that. So the topic is actually embodied carbon. Is it more than just a complexity or an opportunity for a truly contemporary design approach?
That's my waffle.
Sorry. No, it's a good topic. I've just pasted it in, so just please put that into your test sheet. So for question 1, where is the majority of embodied carbon in buildings?
Structure.
Well, structure. When in the design process, question 2, when in the design process, the majority of embodied carbon locked in?
Early.
Concept. Sorry?
Early. So that's the start of a project.
Concept and schematics. What is the relationship between embodied carbon in facades and operating carbon in buildings? And the answer is more embodied carbon in facade solid areas and shading can reduce operating carbon compared to glass facades. And before people run away, you do not need to send me your test sheet. I will be sending you your certificate within the next 24 hours. So you don't need to send me your test sheet. Question 4, what is causing this change and what impact does it have on decision-making moving forward? The grid is greening, reducing, operating, not embodied, making embodied, an increasing slice of the remaining carbon impact of buildings.
And as Carolyn says there on the chat, right now in this decade, we need to decarbonize hugely. So the low upfront carbon is really important.
Spot on. Last question, question 5. What is the difference between operating, embodied, and whole of life carbon? Operating is post-occupation. Carbon embodied is the materials we build from, and therefore life in the project. Whole of life is both together.
See that Letty diagram on slide something early.
People can figure it out.
Yep.
Thank you so much, Paul. Really was so enjoyable. Our biggest and definitely our best presentation yet. I'll let you get back to your week. And yeah.
Thanks very much.
We'll chat soon.
People have asked Steve whether or not this presentation is recorded and will be shared.
Yes. Yeah, so this presentation has been recorded. Everyone will get a recording within the next 6 hours as it processes. And then everyone will get their certificates within the next 24 hours. It'll be uploaded to our YouTube channel, and I'll make sure to send you a copy as well.
Thanks very much.
Awesome. Thanks, guys.
Bye.
You can just close your browser.